There is a question that has followed humanity for as long as we have been able to look up, not a dangerous question, not an urgent one, in the way that hunger or disease is urgent, but a persistent one. A question that has a way of surfacing in the quietest moments, late at night, when the sky is clear and the noise of ordinary life has settled down almost nothing, and you find yourself looking at a field of light so vast and so old that the brain cannot truly hold it. The question is simple. Where is everyone? The universe is approximately 13.8 billion years old. It contains, by current estimates, somewhere between 1 and 2 trillion galaxies. Each of those galaxies contains, on average, hundreds of billions of stars. Many of those stars, we now know with certainty, are orbited by planets, and a significant fraction of those planets orbit within the zone where liquid water, the molecule that life on Earth depends on, could exist on surface. When you do the arithmetic, even conservatively, the number of potential homes for life in the observable universe becomes so large that it loses ordinary meaning. It becomes a number you can write down but cannot truly imagine, a number that, when you sit with it long enough, begins to feel like an argument that we should not be alone. And yet, every radio telescope we have aimed at the sky has returned, on balance, silence. Every search for structured signals from distant stars has come back empty. Every attempt to identify the unmistakable signature of an intelligence operating at a scale beyond our own has, so far, produced nothing conclusive. The universe is full of noise, pulsars, quasars, the ancient microwave echo of the Big Bang itself. But none of it, as far as we can determine, was made by a mind. This is not a small fact. It is arguably one of the most significant facts in the history of science. And it has a name, the Fermi Paradox. The physicist Enrico Fermi put the problem in its most direct form in 1950, during a lunch conversation at Los Alamos National Laboratory. Fermi had been discussing the probability of extraterrestrial civilizations with colleagues, and the numbers suggested that intelligent life should be abundant. The galaxy is old enough that a civilization which had arisen even a few 100 million years before us would have had time, if it chose, to spread across every star system in the Milky Way. And yet, looking around, listening around, there is no trace of it. No signals, no visitors, no evidence of any project, any structure, any transformation of the natural world that could only be explained by intent. Fermi's question was not, do aliens exist? His question was more pointed than that. If the conditions for life are common, and if even a small fraction of life eventually becomes intelligent, and if intelligent life tends to expand and build and use energy at increasing scales, then the galaxy should by now be full of their work, full of something we could see, something we could detect, and we detect nothing. This is the silence at the heart of everything that follows. But before we try to explain that silence, we need to understand what exactly we have been looking for, because in the last 65 years, a specific idea has come to define one of our most ambitious strategies in the search for extraterrestrial intelligence. An idea born in a single short paper published in a scientific journal in the year 1960. An idea about what the most powerful civilization in a star system might build. An idea called the Dyson Sphere. We should be honest about the scale of what we are asking when we ask about advanced civilizations. We are not asking whether life exists elsewhere. That question, while still open, is increasingly likely to receive a positive answer as our instruments improve and our understanding of biology deepens. What we are really asking is something more specific and more unsettling. We are asking whether intelligence, structured, problem-solving, tool-building intelligence, arises elsewhere, and whether, if it does, it survives long enough to do something visible. Consider the arc of human history as a guide, not as a template, but as a single data point. We began as a species entirely dependent on fire and muscle and the chemical energy stored in wood. For most of human history, the amount of energy available to an individual or a community was severely limited by what they could gather, grow, and burn. Then, in the span of about 200 years, we began accessing the energy locked in fossil fuels. the compressed sunlight of hundreds of millions of years of geological time, and our civilization underwent a transformation so rapid that it has no parallel in our species' past. We are now, collectively, consuming roughly 18 terawatts of power. That is 18 trillion watts every second, continuously. It is an enormous number by any human standard. Powered by coal, by oil, by natural gas, by nuclear reactors, by wind turbines and solar panels, spreading across plains and deserts and rooftops. And yet, when you compare it to what is available, it is almost nothing. The sun, our sun, a perfectly ordinary star in the outer arm of a perfectly ordinary galaxy, emits approximately 3.8 times 10 superscript 2 watts. That is a 38 followed by 25 zeros. The energy flowing out of our star every single second is more than all of human civilization has consumed across the entirety of recorded history, many times over. It is energy of a scale so vast that no analogy quite captures it. The sun produces, in a single second, more energy than humanity currently uses in roughly 685,000 years. Almost none of it touches us. Earth intercepts only about 1/2 billionth of the sun's total output. Everything else radiates outward in all directions, passing through empty space forever. And the question that one remarkable physicist asked himself in 1960 was, what would a civilization do if it eventually decided it did not want to waste that energy? Freeman Dyson was not the kind of scientist who stayed inside neat disciplinary boundaries. Born in Crowthorne, England in 1923, Dyson established himself early as a physicist of rare technical brilliance. He made fundamental contributions to quantum electrodynamics, helped design early nuclear reactors, and spent decades at the Institute for Advanced Study in Princeton, one of the most intellectually rarefied environments in the world. But what distinguished him from many of his peers was not only the depth of his technical thinking, it was the breadth of his curiosity and a willingness to follow questions into territory that many scientists found uncomfortable. In 1960, a new kind of conversation was beginning within science. The previous year, physicists Giuseppe Cacconi and Philip Morrison had published a short but transformative paper in the journal Nature, arguing that if extraterrestrial civilizations existed, the most efficient way to communicate across interstellar distances would be through radio waves. Specifically, in a frequency band near 1420 megahertz, the emission frequency of neutral hydrogen, which any radio-capable civilization would presumably recognize as significant. Their paper helped launch what would become the formal search for extraterrestrial intelligence, known as SETI. Dyson read this discussion and began thinking differently about the problem. Most of the early SETI reasoning assumed that extraterrestrial civilizations would want to communicate, that they would be transmitting signals, and that our job was simply to build better receivers and listen more carefully. But Dyson was drawn to a different question. What about a civilization that was not trying to be heard? What if the most advanced civilizations in the galaxy had no particular interest in announcing themselves to younger species? How would you detect something that was not attempting to be detected? His answer was elegant and, in retrospect, obvious. You would look for what they built. Dyson's paper, published in the journal Science in June 1960, was titled Search for Artificial Stellar Sources of Infrared Radiation. It is a remarkable document, not because it is long or mathematically complex, but because it is neither. The entire paper fits on less than 2 pages. It is an act of imaginative reasoning compressed into the space of a brief argument, and it has been generating discussion ever since. The core insight was this: a civilization with access to advanced technology and a need for energy would, over time, be driven to capture an increasing fraction of its star's output. On Earth, we harvest a fraction of 1% of the sunlight that strikes our planet. But imagine a civilization 10,000 years ahead of us, or 100,000 years, or a million. Such a civilization would face a hard physical constraint. If your energy needs keep growing and your star is the largest available source of energy in your vicinity, you would eventually be motivated to harvest not just a small portion that strikes your planet, but a significant fraction of the total output. Dyson's original proposal was not a solid shell enclosing the star. That design, which became the popular science fiction image of the Dyson Sphere, is actually considered physically impossible. What Dyson described was a swarm of individual structures, satellites, collectors, habitats, orbiting the star and collectively intercepting its energy, transmitting it back for use. In fact, Dyson himself later acknowledged that the name attached to the concept was perhaps misattributed. He admitted to basing his concept on a 1937 science fiction novel, Star Maker, by British writer Olaf Stapledon, writing later that some science fiction writers have wrongly given me the credit of inventing the artificial biosphere. In fact, I took the idea from Olaf Stapledon. In Star Maker, Stapledon described a gauze of light traps surrounding every star in the universe, which focused escaping solar energy for intelligent use. The image was poetic, and Dyson made it scientific. But it was Dyson who asked a crucial follow-up question that turned a science fiction image into a search strategy. If such a structure existed around a distant star, if a civilization had, over centuries or millennia, assembled a vast cloud of energy-collecting structures surrounding their sun, what would it look like from Earth? His reasoning was straightforward. All structures absorb energy and radiate it as heat. The second law of thermodynamics is absolute on this point. You cannot capture and use energy without generating waste heat. A star surrounded by a swarm of energy collectors would still emit the same total amount of energy as before. But instead of emitting it as visible light, it would re-emit it at a lower temperature, in the infrared part of the spectrum, as heat, from a distance. Instead of seeing a bright star, you would see what appeared to be an anomalously dim optical source with an unexplained excess of infrared radiation. In his 1960 paper, Dyson indicated that these structures could be detected based on the waste heat they emitted at mid-infrared wavelengths. And to this day, infrared signatures are considered a viable techno-signature in the search for extraterrestrial intelligence. This was the birth of a new field within SETI, the search not for radio signals, but for heat, for the thermodynamic footprint of industry operating at the scale of a star. To understand why this idea carries such weight, it helps to place it within a broader framework that was being developed at almost exactly the same time, on the other side of the planet. In 1964, Soviet astrophysicist Nikolai Kardashev published a paper that proposed a classification system for technological civilizations based on one simple criterion: how much energy do they use? Kardashev proposed a classification of civilizations into three types based on the principle of exponential growth. A Type 1 civilization is able to access all the energy available on its planet. A Type 2 civilization can directly consume a star's energy, most likely through the use of a Dyson Sphere. A Type 3 civilization is able to capture all the energy emitted by its galaxy and every object within it. The Kardashev scale, as it became known, was not a claim about what civilizations actually exist. It was a framework for thinking about the range of possibilities, a kind of map for the search, and it gave the Dyson Sphere concept a formal position in scientific reasoning. The construction of such a structure will be the defining project of a Type 2 civilization, the marker of a species that had fully crossed from a planetary to a stellar scale of operation. Where are we on this scale? Humanity is currently subtype I, roughly type 0.7 on Carl Sagan's fractional extension of the scale. Global energy consumption is approximately 18 terawatts, roughly 1,000 times less than the Type 1 threshold of approximately 10 superscript 1 watts. We have not yet fully harnessed our own planet. We are nowhere near harnessing our star. But the Milky Way is approximately 13.6 billion years old. Stars capable of supporting life have been forming for billions of years. If a civilization had arisen around one of those older stars and followed a trajectory even broadly similar to ours, growing, developing technology, consuming more energy, the most advanced of them would have had billions of years of head start. Billions of years. That is enough time for a civilization to not merely build a Dyson Sphere, but construct one, use it collapse, re-emerge, and do again many times over. It is enough time for multiple independent civilizations to have transformed multiple star systems in ways that should be detectable across interstellar distances. This is what makes the silence so striking. Not that we haven't found a Dyson Sphere yet. We have only been looking, in any serious sense, for about 60 years, and only with instruments capable of the task for a fraction of that time. What is striking is that the universe, across the billions of years it has had to fill with the project of ambitious minds, appears, so far, to have left no obvious marks. Let's be precise about what a Dyson Sphere, or more accurately a Dyson swarm, would actually require to build. We will use our own solar system as a reference point, because it is the only planetary system we know in detail. The Sun produces approximately 3.86 times 10 superscript 2 watts. To capture a substantial fraction of that output, you would need to cover an enormous area. A sphere centered on the Sun at, say, roughly the distance of Earth's orbit, 1 astronomical unit, would have a surface area of approximately 2.8 times 10 superscript 2 superscript 3 square meters. That is about 550 million times the total surface area of Earth. The raw material for such a structure would need to come from somewhere. The most discussed candidate is a disassembly of the non-stellar mass of the solar system, the planets, moons, and asteroids. Jupiter alone, the largest planet, contains about 1.9 times 10 superscript 2 kilograms of mass. Building a Dyson Sphere or a Dyson swarm will require grinding up a significant fraction of the planets in your solar system for building materials. It is, by any measure, an engineering project of a scale that dwarfs anything in human history. And yet, from a physics standpoint, nothing about this violates any known law. There are no equations that forbid it. The materials exist. The energy to do the work would, at some point, be available from the structure itself as it came online in sections. The timeline would be measured in centuries, perhaps millennia. But for a civilization that had achieved technological stability and had a reason to undertake the project, it is not, in principle, impossible. This is what makes the Dyson Sphere different from many other concepts discussed in the context of the search for extraterrestrial intelligence. It is not speculation about physics we do not yet understand. It does not require faster-than-light travel or exotic energy sources, or any technology that is fundamentally beyond what our current science allows us to imagine. It requires patience, resources, and an organizing principle. Given enough time, a sufficiently advanced civilization operating entirely within known physics could build one. And if they built one, we should, in principle, be able to see it. Here is the philosophical dimension that tends to get lost in the technical discussion. When Dyson published his paper in 1960, he was not making a bold claim about the universe. He was asking a question about the relationship between intelligence and energy, a question that applies to us as much as to anyone else. He was pointing out that intelligence, as we understand it, tend to organize matter and energy in increasingly complex ways. That is, in a sense, what intelligence does. It takes available energy and uses it to build structures that did not exist before. And if that tendency holds, and if it continues, then somewhere along the line, if civilization persists long enough, the scale of that building must eventually reach the stars themselves. Dyson was also implicitly raising a question about what we should expect to see in a universe filled with civilizations. He was arguing that the most advanced civilizations would not announce themselves through radio signals, because a civilization operating at a stellar energy scale might have moved well beyond the radio age. It would not communicate across a galaxy with the equivalent of a technological toddler's walkie-talkie. It would be detectable, if at all, by the thermodynamic signature of its infrastructure. This shift in thinking was significant. It moved the search from listening for a message to looking for a city, or rather, for something so large a city is to what a single brick is to a city. There is something quietly humbling about that idea. Because if a civilization has built a Dyson Sphere, they are not thinking about us. They are not sending messages into the void, hoping some young species notices. They are engaged in an engineering project a scale of which we cannot experience except through calculation. We are the radio era listeners hoping to catch a signal from civilizations for whom radio was a brief and primitive phase, long since surpassed. The silence in that framing is not necessarily emptiness. It might simply be that we have not yet learned to see what is there. But seeing it requires instruments. It requires surveys. It requires strategy for distinguishing a warm alien megastructure from the many natural astrophysical objects that also glow in the infrared. And that is where the story moves in its second chapter. To the telescopes, the data pipelines, the neural networks, and the 7 candidates that briefly, in 2024, made headlines around the world. The search had, at long last, turned up something worth looking at. Whether that something was what anyone hoped it was, that is a different matter entirely. Science is, at its core, a discipline of patience, not the patience of waiting for something to happen, though that is sometimes required too, but a more specific kind of patience, the patience of designing a method, building an instrument, and then trusting the method and the instrument enough to follow where the data leads, even when the data does not say what you hoped it would say. The search for Dyson spheres is, in this respect, a very good example of science working exactly as it should. Over the 6.5 decades since Freeman Dyson published his 2-page paper in 1960, the field has evolved from a thought experiment into a structured research program with specific instruments, specific data pipelines, specific criteria for what counts as a candidate and what counts as a false alarm. And it has done this in the face of consistent silence. Not discouraging silence, necessarily. The silence of a forest at night is not the same as the silence of an empty room. But silence nonetheless. No confirmed detection. No unambiguous signal. No star that, after thorough investigation, has refused any natural explanation and forced a conclusion that something was built there. To understand why the search is as difficult as it is, and to appreciate what researchers have actually accomplished, it helps understand the instruments involved and the problem they're trying to solve. The fundamental challenge of the infrared search can be stated simply. You are looking for a star that glows in the wrong way. A normal star emits light across a broad spectrum of wavelengths, with the peak of that emission determined by the star's surface temperature. Our Sun, with a surface temperature of about 5,778 Kelvin, peaks in the visible part of the spectrum, which is not a coincidence, since life on Earth evolved eyes tuned to the dominant radiation of its parent star. Cooler stars peak in the infrared. Hotter stars peak in the ultraviolet. When you look at a star with an infrared telescope and find that it has significantly more infrared emission than its surface temperature would predict, that is called an infrared excess. It means something is radiating in the infrared that is not the star itself. In most cases, this something is warm dust, material orbiting the star that has been heated by stellar radiation and re-emits that energy at longer wavelengths. This is already happening in our own solar system, to a minor degree. The zodiacal light, that faint glow sometimes visible near the horizon after sunset, is partly caused by dust scattered through the inner solar system, warmed by the sun and radiating in the infrared. Around younger stars, this phenomenon is far more pronounced. A star with a debris disk, a broad cloud of dust and rocky material left over from planetary formation, or produced by the ongoing collision of asteroids and comets, can show a significant infrared excess. And here's the problem. A partial Dyson sphere, a swarm of structures covering, say, 20 or 30% of the star's surface area, would look, in its infrared signature, not entirely unlike a debris disk. Both are structures orbiting a star. Both absorb visible starlight and re-emit it as heat. Both produce an excess of infrared radiation. The spectral energy distributions, the graph showing how much energy is emitted at each wavelength, can, in some cases, be difficult to distinguish without additional data. This is not an insolvable problem. A Dyson sphere and a debris disk have different expected properties. A Dyson sphere will be highly efficient at absorbing light. Structures built to harvest energy should cover a large fraction of the star's luminosity. A debris disk would typically be much more diffuse. The temperature profile, the fractional luminosity, the fraction of the star's total energy that is being intercepted, and the geometry of the emission can all, in principle, help distinguish one from the other, but they require high-quality data and careful analysis to do so, which is where the telescopes come in. The instrument that has done the most to define modern Dyson Sphere searches is the Wide-Field Infrared Survey Explorer, known as WISE. WISE was a NASA infrared astronomy space telescope launched in December 2009. It performed an all-sky survey at 4 infrared wavelength bands, 3.4, 4.6, 12, and 22 micrometers, producing a catalog that covered the entire sky. The mission was originally planned to last about 10 months before its cryogenic coolant was exhausted. The spacecraft was eventually deactivated in August 2024, having operated in various modes for nearly 15 years. First as WISE completing its all-sky infrared survey, then reactivated in 2013 under the name NEOWISE for asteroid tracking. The significance of those 4 wavelength bands requires a brief explanation. The shorter wavelengths, 3.4 and 4.6 micrometers, are where you see the genuine infrared emission from star surfaces and warm dust in the immediate stellar environment. The longer wavelengths, 12 and 22 micrometers, are where excess heat emission would be expected from a structure with the kind of temperature profile a Dyson Sphere would produce. Dyson himself estimated, in his original 1960 paper, that a structure at roughly twice Earth's distance from a sun-like star would have a temperature of around 200 to 300 Kelvin, and such a temperature corresponds to emission that peaks right in that mid-infrared range. WISE, in other words, was not designed to search for Dyson spheres. It was designed to survey cool objects, brown dwarfs, nearby stellar systems, luminous galaxies across the universe. But the wavelengths it covered happened to be exactly where Dyson Sphere waste heat would appear. The data was there. It simply needed to be analyzed with that question in mind. The second crucial instrument in the modern search is Gaia, the European Space Agency's astrometry mission. Gaia was launched in December 2013, and over the course of its operational lifetime measured the positions, distances, and motions of approximately 1 billion stars across the Milky Way. It did this through parallax, measuring the tiny apparent shift in the star's position as Earth moves around the Sun, a shift that is larger for nearby stars and smaller for distant ones. Why does distance matter for a Dyson Sphere search? Because to know whether a star has an infrared excess, you first need to know what its normal emission should be. And to know that accurately, you need to know the star's intrinsic luminosity, how bright it actually is, as opposed to how bright it appears from Earth. That requires knowing the distance. Without an accurate distance measurement, the entire analysis becomes unreliable. Gaia's contribution was to provide, for the first time, highly precise distances to hundreds of millions of stars, distances precise enough to anchor the kind of detailed comparison that a Dyson Sphere search requires. Gaia's science observations ended on January 15th, 2025, and the spacecraft was permanently decommissioned on March 27, 2025. 2 major data releases are still forthcoming. Data Release 4, planned for 2026, and the final data, Release 5, planned for around the end of the decade. The combination of WISE's all-sky infrared photometry and Gaia's precise stellar distances is what made systematic searches for Dyson spheres possible for the first time. There was one additional element required: a method for filtering through the data. 5 million stars is not a number that can be reviewed by human eyes. When researchers began building pipelines to search for Dyson Sphere candidates, they confronted a problem familiar to anyone working in modern observational astronomy. The datasets are vast, the signals are subtle, and the universe is full of natural phenomena that can mimic, in one way or another, the signature you are looking for. To address this, the researchers behind Project Hephaestos, a systematic Dyson Sphere search conducted at Uppsala University in Sweden, developed a multi-stage filtering pipeline that combined conventional astrophysical criteria with modern machine learning techniques. The name Hephaestos, incidentally, comes from the Greek god of fire, metalworking, and craftsmanship, the smith of the gods, the maker of extraordinary structures. It is a fitting name for a project dedicated to looking for the ultimate engineering achievement. The pipeline began with a full combined dataset from Gaia Data, Release 3, the 2-mass infrared sky survey, a catalog of nearly all stars visible in the near-infrared, and the WISE All-Sky Survey. From the starting point of hundreds of millions of objects, the team applied a series of filters designed to narrow the field. First, they restricted the search to stars within 300 parsecs of Earth, approximately 980 light-years. This was not because Dyson spheres would only exist close to us, but because the quality of both the infrared photometry and the distance measurements degrades at greater distances. Beyond 300 parsecs, the data becomes too uncertain to distinguish a genuine infrared excess from measurement noise. The choice was methodologically conservative. It meant they were searching a small sphere around a location in the galaxy, but searching it reliably. Second, the team focused on objects with detections in the longest wavelength-wise bands, the 12 and 22 micrometer channels, labeled W3 and W4 in the WISE catalog. These are the bands most sensitive to the kind of mid-temperature waste heat a partial Dyson sphere would produce. Third, and this is where the technology becomes interesting, the pipeline incorporated a convolutional neural network, a type of machine learning architecture originally developed for image recognition, to identify cases where the WISE data was confused or contaminated by nearby sources. WISE had a spatial resolution of about 6 to 12 arcseconds, a relatively coarse field of view compared to optical telescopes. This meant that in dense areas of sky, or in regions where background objects happened to lie close to a target star in projection, the infrared measurements could be picking up light from something other than the star under study. The neural network was trained to flag such cases and remove them from the candidate pool. After all filtering was complete, the pipeline identified 7 candidates deserving of further analysis, all of which were M-dwarf stars exhibiting an infrared excess in the WISE W3 and W4 bands. 7 out of 5 million. That number, 7, is worth sitting with for a moment, not because it is large. It is, by any measure, a tiny fraction, but because the process that arrived at it was rigorous. These were not 7 objects selected by eye or flagged on intuition. They were the residue after a systematic elimination of everything with a plausible natural explanation. They were the anomalies that remained after the field had been searched as carefully as the available instruments allowed. Before we look at those 7 candidates in detail, it is worth saying something about what the search found on the way, which is to say, what confirmed it did not find, one of the outputs of Project Hephaestos, and of similar surveys conducted before it, is not just a list of candidates. It is an upper limit. An earlier phase of the project, published in 2022, analyzed more than 100 million stars from Gaia and WISE, and established that at most roughly 1 in 100,000 objects in the most favorable search conditions could host a partial Dyson sphere. And even this estimate is likely to be a significant overcount, since many natural phenomena can mimic the signature. An upper limit is a statement about what can be ruled out. It says, given the data we have, if Dyson spheres were common, if 1 in 1,000 stars had 1 or 1 in 10,000, we would expect to have found many clear examples by now. The fact that we have not found any unambiguous examples suggests that if Dyson spheres exist at all in the part of the galaxy we have searched, they are extremely rare. This is a result in itself. It narrows the space of possibilities. It does not prove that Dyson spheres do not exist, but it places quantitative constraints on how common they can be. The philosophical weight of this finding deserves acknowledgement. We have looked at millions of stars within roughly 1,000 light-years of Earth and found nothing that clearly requires an artificial explanation. That is a statement about the universe. It may be a statement about the rarity of civilizations capable of such construction, or it may be a statement about the limitations of our instruments and our search strategy, or both. We will return to that question in Part 3. For now, the 7 remain. In May 2024, a paper appeared in the monthly notices of the Royal Astronomical Society. Its title was precise and technical: Project Hephaestos 2, Dyson Sphere candidates from Gaia DR3, to mass, and wise. Its authors were a team of astronomers from Uppsala University, led by Matthias Suazo, working alongside infrared and SETI specialists, including Jason Wright of Pennsylvania State University, who has been one of the most methodical and scientifically careful voices in the field of technosignature research. The paper described what the pipeline had found. 7 stars, all red dwarfs. More precisely, all M-type main sequence stars, the most abundant class of star in the galaxy, smaller, cooler, and dimmer than our sun, burning hydrogen slowly and capable of lives 10 to 100 times longer than our star's 10 billion year lifespan. All 7 showed the same general pattern. In the optical and near-infrared, the wavelengths that reflect the actual surface emission of the star, they look like perfectly normal M dwarfs. But in the mid-infrared bands, the 12 and 22 micrometer channels wise, they glowed more brightly than they should. The excess could not, in the most straightforward analysis, be explained by the star itself. The characteristics of these candidates challenge natural explanations. Debris disks around M dwarfs are extremely rare, and these candidates showed higher temperatures and larger fractional luminosities than typical debris disks. While young stellar disks can have larger fractional luminosities, the 7 candidates lack the variability typically associated with young stars. This last point is significant. Young stars still in the process of clearing out their surrounding disk of dust and gas, do show strong infrared emission, but they also vary in brightness because the disk is dynamic. Dust clumps and disperses, material falls inward or is blown outward by stellar winds, and the resulting changes in obscuration produce brightness fluctuations that can be detected over weeks or months. The 7 candidates were not varying in this way. They appeared stable, which is what you would expect from a debris disk that has settled into a steady-state configuration, or from a persistent artificial structure. But a settled debris disk around an M dwarf of the age these stars appear to have been much cooler and dimmer in the infrared than what was observed. The paper concluded that these 7 objects deserved follow-up, not that they were Dyson spheres. The authors were careful and specific about this, as any responsible scientist would be. The conclusion was that the infrared excess was anomalous, that the most common natural explanations were inadequate to fully account for it, and that more data was needed. The scientific community was reminded that extraordinary claims require extraordinary evidence, and that the history of SETI includes many false alarms and misinterpretations. Nevertheless, the identification of these 7 Dyson Sphere candidates was described as a significant milestone in the field. The press picked up the story. Headlines announced that astronomers had found possible alien megastructures. Science communicators wrote explainers. Enthusiasts made videos. For a brief period, 7 faint red stars, scattered across the sky within about 1,000 light-years of Earth, became the most talked-about objects in popular astronomy. And then the follow-up papers arrived. Science does not pause for headlines. While the popular coverage of the Hephaistos findings was still reverberating, other research groups were already working on the same 7 stars, bringing different data and different methods to bear on the same anomalies. The first significant challenge came quickly. A separate team cross-referenced the positions of the 7 candidates against the catalogs of multiple radio sky surveys, the Very Large Array Sky Survey, the Rapid Escape Continuum Survey, the First Survey, the NRAO VLA Sky Survey, and others. They were looking for a radio emission coincident with the 7 stars, because a genuine stellar system with an active Dyson Sphere would not be expected to produce strong radio emission, while certain types of background objects, in particular, radio-loud galaxies with active nuclei, most certainly would. What they found was revealing. Radio emission was detected associated with 3 of the 7 candidates, labeled A, B, and G. For candidate G, the radio source had a steep spectral index consistent with synchrotron emission from a radio-loud active galactic nucleus with extended jets. An active galactic nucleus is a galaxy with a supermassive black hole at its center that is actively accreting material and emitting radiation across the electromagnetic spectrum. These objects can be extraordinarily bright in the mid-infrared, precisely because the hot dust surrounding the central engine glows intensely at those wavelengths. The radio detection was a clue, It suggested that for at least some of the Hephaestos candidates, the mid-infrared excess might not be coming from the M dwarf star at all. It might be coming from something behind the star, a background galaxy that happened to lie along the same line of sight. Its emission blended with the stellar signal by WISE's relatively coarse spatial resolution. The investigation of candidate G went further. Analysis of the WISE imaging showed that while the positions of the emission in the shorter wavelength WISE bands W1 and W2 were consistent with the known location of the M dwarf star, the positions in the longer wavelength W3 and W4 bands, the very bands showing the anomalous excess, were offset by several arcseconds toward a separate radio source. An arcsecond is a very small angle, 1/3600th of a degree, but several arcseconds is enough of a displacement, when measured carefully with precise instruments, to indicate that two different objects are being confused. The shorter wavelengths were seeing the star. The longer wavelengths were seeing something else, something behind it. That something was identified as a background galaxy of a specific and unusual type. The proposed contaminant belongs to a class of objects called hot dogs, hot, dust-obscured galaxies. These are extremely luminous galaxies powered by rapidly accreting supermassive black holes surrounded by hot dust, and they are detected as strong sources at precisely the mid-infrared wavelengths where the Hephaestos candidates showed their anomalous excess. Hot dogs have a surface density of approximately 1 per 31 square degrees of sky, which the authors showed was sufficient to account for the level of contamination seen in a survey examining 5 million stars across the full sky. In other words, the universe contains a population of objects, distant hyperluminous dust-shrouded galaxies, that glow brilliantly at exactly the wavelengths where Dyson spheres would also glow, and WISE, with its limited spatial resolution, cannot always cleanly separate the light of a nearby M dwarf from the light of a hot dog galaxy billions of light years behind it, sitting just a few arcseconds away in projection. The researchers proposed that all 7 Dyson Sphere candidates reported by Hephaestos had very likely been misidentified, with their spectral energy distributions being significantly contaminated by background hot dogs in the WISE W3 and W4 bands. The conclusion was not that the Hephaestos team had made an error. Their pipeline had done exactly what it was designed to do: identify stars with anomalous infrared emission that could not easily be explained by known astrophysical processes. The confusion with background galaxies was a limitation of the underlying data, not of the analysis. WISE's spatial resolution was not fine enough to resolve the ambiguity in the contamination class. Hot dogs had not been fully appreciated as a source of false positives in stellar infrared surveys of this kind. As one researcher noted, the development of new astronomical instruments does not follow the rapid update cycles of consumer electronics. It takes decades. WISE was launched in 2009 and expired in 2024. Gaia was launched in 2013 and decommissioned in March 2025. The next generation of comparable probes may not be available for a long time, making it unlikely that a large-scale Dyson Sphere search program like Project Hephaestos will be conducted again in the near future. The current 7 Dyson Sphere candidates, whatever they turn out to be, deserve careful examination precisely because of that constraint. Where does this leave the 7 candidates? The honest answer is unresolved. The contamination hypothesis that some or all of the 7 are M dwarfs whose WISE photometry was corrupted by background hot dog galaxies is well supported by the available evidence, particularly for candidate G, where the positional offset was directly measured. For the remaining 4 candidates where no radio emission was detected, the situation is less clear. They may be radio-quiet hot dogs. They may be other classes of background source. They may have natural astrophysical explanations not yet fully characterized. What they almost certainly are not, based on the way of the evidence, is evidence of Dyson spheres. But they are not nothing either. They are a demonstration that the search methodology works, that anomalies can be found at scale, and that distinguishing genuine technosignatures from natural phenomena is going to require better instruments than the ones we currently have. The 7 candidates illustrate something important about how scientific investigation actually proceeds. A result is announced. The community responds. Alternative explanations are examined. The specific claim is weakened or refuted, but the underlying methodology is refined and improved. The next search will be better than the last one because of what was learned from the failure, or rather, from the qualified result of this one. This is not the dramatic arc of science fiction, in which a discovery is made and everything changes at once. It is the actual arc of science, slower, more ambiguous, more cumulative. Progress is not measured in confirmed discoveries. It is measured in the quality and precision of the questions you are now able to ask. There is something else worth drawing out of the Hephaestus story that goes beyond the specifics of these 7 stars. The fact that hot dog galaxies, objects billions of light years away, among the most luminous things in the observable universe, powered by supermassive black holes consuming matter at extreme rates, can contaminate a search for structures around nearby stars is not a footnote. It is a reminder of how complex the universe is, and how many different kinds of things are emitting energy at any given wavelength. When you look at a star and find it glowing in the infrared, the list of possible explanations includes warm circumstellar dust, a young stellar disk, tidal disruption events, binary companions, and sitting in projection behind the star, separated from it by hundreds of millions of light years of empty space, but appearing to be in the same pixel, the glare of a galaxy whose central engine burns as brightly as 100 trillion suns. The universe does not make it easy, and yet the search continues, because the alternative, assuming that the silence is permanent, that nothing is out there to find, that the universe is large and old and full of stars and utterly devoid of the works of minds, is not a conclusion the evidence supports. It is simply the default state of ignorance. We have not found a Dyson Sphere, but we have built, for the first time, a systematic method for looking. We have searched 5 million stars within 1,000 light years of Earth and set quantitative upper limits on how common such structures can be in our cosmic neighborhood. We have identified the contamination sources that will confuse future searches if they are not accounted for. We have written papers, refined pipelines, and built a foundation of methodology that did not exist 20 years ago. The search is, in the strictest sense, just beginning, but there is a third chapter to this story. And it does not begin with a database of 5 million objects. It begins with a single star, a star with a name that does not sound like the name of a mystery, but which became, for a period of several years, the most discussed and most scrutinized object in all of observational astronomy outside the solar system. A star that dimmed, and then dimmed again, and then dimmed a third time, by 22% of its total light. A dimming so large that no natural explanation at hand could account for it. A star that inspired more speculation, more papers, and more heated scientific debate than almost any other object in recent astronomical history. A star called KIC 846-2852, but the world knew it by a different name. In September 2015, a team of astronomers led by Tabby published a paper in the monthly notices of the Royal Astronomical Society with an unusual subtitle. Where's the flux? The star described was catalogued as KIC 846-2852, discovered through data from NASA's Kepler Space Telescope by citizen scientists participating in the Planet Hunters project. Within the scientific community, it became known informally as Tabby star, after its discoverer. What Kepler had recorded was, at the time, unlike anything previously documented in stellar observation. A star does not simply go dark by 22%. Planets cross in front of stars and cause dips. But even the largest planet orbiting a sun-like star would block, at most, about 1% of its light. 22% requires something vastly larger, or something distributed and complex, orbiting between the star and the observer. The pattern of the dimming made it stranger still. It did not repeat on a fixed schedule as a planet's transit would. The dips came at irregular intervals, varied in depth, and lasted from days to weeks. Kepler's 4 years of data showed multiple episodes of anomalous dimming, each different in shape from the last. And separately, discovered from historical photographic plates. The star appeared to have faded overall by roughly 14% between 1890 and 1989, and have continued fading at a measurable rate during the Kepler mission itself. Not just dipping, fading, slowly, persistently, over a timescale of a century. This combination, dramatic short-term dips and long-term secular dimming, had no immediate precedent. Astronomers proposed explanations in quantity: a swarm of comets perturbed by a passing star, a recent collision between large planetary bodies, producing a debris cloud, a captured asteroid field, the system undergoing its own version of the late heavy bombardment, the period roughly 4 billion years ago in our solar system's history, when the inner planets were subjected to an intense barrage of impacting objects, and, inevitably, the hypothesis that the internet would amplify to a global level an alien megastructure, a partial Dyson sphere, or a vast array of solar collectors, orbiting the star and blocking its light. The megastructure hypothesis was never the favored explanation among working astronomers, but it was not dismissed out of hand either. Jason Wright of Penn State, one of the researchers who had thought most carefully about what technosignatures would look like, noted publicly that the dimming pattern was consistent with, though not uniquely explained by, a swarm of artificial structures. The SETI Institute pointed the Allen Telescope Array at KIC 846-2852 to search for radio signals. None were detected. The key piece of evidence that effectively ruled out opaque megastructures, and with them most solid or large-grain blocking objects, came from multi-wavelength observations conducted during several dimming events caught in real time in 2017 and 2018. The dimming was found to be wavelength dependent. Blue light was blocked more strongly than red light, in a pattern consistent with fine dust particles. A solid, opaque object, whether a planet, an asteroid, or a megastructure, would block all wavelengths of light equally. The wavelength dependence pointed clearly toward material with grain sizes at or below the micrometer scale. Dust. This conclusion, that dust of some kind is a proximate cause of the short-term dips, is the current scientific consensus. What remains genuinely uncertain is the origin of that dust. Several hypotheses have been advanced and none definitively confirmed. One proposal, supported by Spitzer and Swift observations, as well as data from the Belgian Astrolab Iris Observatory, attributes the long-term dimming to an uneven cloud of dust in orbit around the star, moving slowly across the line of sight. Another, published in 2017 by Meng and colleagues, concluded that only microscopic fine dust screens originating from circumstellar material could account for the wavelength-dependent dimming observed. A more detailed mechanistic hypothesis was published in 2019 by astrophysicist Brian Metzger, Miguel Martinez, and Nicholas Stone of Columbia University. They propose that the short-term dips and the long-term secular dimming can both be explained by the disruption of an exomoon, a moon orbiting a planet that has migrated closer to the star due to tidal forces. As the moon's orbit decays and approaches the star, it heats up, ice vaporizes. Carbonaceous rock and larger grain material is shed into space, inheriting the exomoon's orbit. This debris accumulates into a disk surrounding the star, which persistently blocks a fraction of starlight, producing the long-term dimming, while the irregular passage of clumps and clouds through the line of sight produces the short-term dips. The model accounts for the slow change in the disk opacity as larger particles gradually spiral inward and smaller grains are blown outward by radiation pressure. The exomoon hypothesis is the most mechanistically complete explanation on the table for Tabby star as of 2025. It is consistent with the available observations. It does not, however, constitute a confirmed answer. No direct detection of the proposed exomoon or its parent planet has been made, and the specific circumstances required. A moon being stripped from its planet and spiraling toward the star on the observed timescale are unusual enough that the proposal remains a hypothesis rather than a conclusion, as the Wikipedia entry on the star noted in 2024. Several hypotheses have been proposed to explain the star's large, irregular changes in brightness, but as of 2024, None of them fully explain all aspects of the resulting light curve. This is the honest state of knowledge. The star is not unexplained in the sense of having no candidate explanations. It has several, some of them well developed. But it remains unexplained in the deeper sense that no single model fits every feature of the data without requiring additional assumptions or leaving residuals that demand further accounting. The alien megastructure hypothesis, meanwhile, has not been formally ruled out by a logical proof. It has been made progressively more implausible by the accumulating evidence for natural explanations, most decisively by the wavelength dependence of the dimming, which is very difficult to reconcile with any opaque artificial structure for the purposes of scientific reasoning. Progressively more implausible is not the same as impossible, but it moves the hypothesis from a category of open questions to the category of unlikely ones. What Tabby's star did for the search for megastructures was not find one. What it did was demonstrate, for the first time at this level of public visibility, that there exist stars in the galaxy with light curves so anomalous that they cannot be immediately explained by any process in the standard astrophysical catalog. The search methodology was tested against a real anomaly and found to produce results worth investigating. The investigation did not confirm an artificial origin, but it showed that such anomalies can be discovered, can be followed up in real time, and can be subjected to systematic multi-wavelength analysis that progressively narrows the field of possibilities. That, in itself, is scientific progress. There is a question that deserves a careful and honest answer. If Dyson spheres are physically possible, and if the galaxy is billions of years old and contains hundreds of billions of stars, and if even a small fraction of those stars have given rise to civilizations capable of eventually constructing such structures, why have we not found one? The honest answer is not a single statement. It is a set of reasons, each independently sufficient to explain the silence, and each worth examining on its own terms. None of them require invoking alien psychology, civilization collapse, or any process we do not understand. They follow directly from the technical reality of the search as it currently exists. The first reason is geography. Project Hephaestos searched for Dyson Sphere candidates within approximately 300 parsecs of Earth, roughly 980 light-years. This was not a conservative choice imposed by timidity or lack of ambition. It was determined by the quality of the data. Beyond that distance, wise photometry and Gaia distance measurements become too uncertain to reliably identify an infrared excess. The search was as far-reaching as the instruments would reliably support. But the Milky Way is approximately 52,850 light-years in diameter. The volume of the galaxy that Project Hephaestos searched, a sphere of radius 980 light-years centered on Earth, represents a tiny fraction of the total galactic volume. If Dyson spheres exist, but are extremely rare, concentrated in the older stellar populations of the galactic core or distributed across the full disk, the survey would simply not have reached them. The absence of detections within 980 light-years is a statement about our local neighborhood, not about the galaxy as a whole. The second reason is instrumentation. The two telescopes that made the Hephaestos search possible, WISE and Gaia, were both decommissioned within months of each other in 2024 and 2025, respectively. WISE ceased operations in August 2024, after nearly 15 years of service. Gaia's science observations ended in January 2025, with the spacecraft permanently decommissioned in March of that year. Two final Gaia data releases are still forthcoming. Data Release 4, planned for 2026, and Data Release 5, expected toward the end of the decade, which will provide more precise stellar distances and may enable refinement of existing candidate lists. But no comparable all-sky infrared survey instrument is currently operational. The spatial resolution of WISE, approximately 6 to 12 arcseconds per pixel, was sufficient for a first survey, but was demonstrated to be a source of false positives when background galaxies fell close in projection to nearby stars. As the contamination analysis of the 7 Hephaestos candidates showed, the very wavelengths most sensitive to Dyson sphere waste heat are also the wavelengths where hot, dust-obscured galaxies billions of light-years away glow most brightly. Separating these two classes of object requires either much higher angular resolution or spectroscopic follow-up of each candidate. Both require significant observing time on large facilities. Future space missions with higher infrared resolution, such as the Roman Space Telescope, planned for the mid-2020s, may eventually provide data that enables a more powerful search. But as of 2025, the observational window opened by WISE and Gaia has closed without an obvious successor in place. The next large-scale Dyson Sphere search will likely require either repurposing of existing facilities or the advent of a new dedicated mission. The third reason concerns assumptions about what we are looking for. The standard Dyson Sphere search strategy assumes that the waste heat of an energy-harvesting megastructure would be radiated as thermal emission in the mid-infrared at temperatures of roughly 200 to 600 Kelvin, corresponding to structures at roughly Earth's distance from a sun-like star. This is a physically motivated prediction, not an arbitrary one, but it is a prediction that assumes we understand how a civilization that builds such a structure would use the energy it captures. A civilization harvesting a large fraction of its star's output might do so with structures that operate at different temperatures, emitting waste heat at different wavelengths. They might use their energy with an efficiency we have not imagined, producing less waste heat than the classical model predicts. They might have built structures around stars very different from the ones we have prioritized. They might have configured their megastructure to minimize detectability, not because they are hiding, but because the engineering optimum happened to produce a low-contrast infrared signature. None of these possibilities require invoking physics we do not understand. They are simply variations on the same basic concept that we have not yet fully explored. The search has been rigorous within the assumptions it has made. Whether those assumptions encompass the full range of possible technosignatures is a separate question. The fourth reason is time. The universe is approximately 13.8 billion years old. Astronomers have been systematically searching for signs of extraterrestrial intelligence in any form by any method for roughly 65 years. Focused infrared searches of the kind described here have been conducted for perhaps 2 decades, and large-scale systematic surveys using modern data pipelines for far less. A 2025 paper in the Open Journal of Astrophysics by Matthew C. Valetti, which constructed a geometric model for the probability of detecting extraterrestrial signals via passive SETI, illustrated the scale of the challenge. The probability of detecting even a single signal from a communicative civilization depends, among other things, on the distance over which that civilization is transmitting. For a galaxy-wide search to have a high probability of success, the number of communicative civilizations in the galaxy would need to be very large. And even then, the geometry of transmission and detection creates significant constraints. The absence of detections over 65 years of SETI, while statistically informative, does not constitute a definitive result on its own. 65 years against 13.8 billion. The comparison is not comforting, but it is honest. These 4 reasons, geography, instrumentation, assumptions, and time, are not excuses. They are calibrations. They define the boundaries of what the search has actually tested, as opposed to what it is not. The absence of detections within those boundaries is genuine information. It constrains the frequency of Dyson spheres within roughly 1,000 light-years of Earth to be low. It tells us that our local stellar neighborhood, searched at the sensitivity available to WISE and Gaia, does not contain any obvious examples of stellar-scale engineering. What it does not tell us is that no such examples exist anywhere in a galaxy containing several hundred billion stars, with history spanning billions of years. Those are different statements. The discipline of the search requires holding them clearly apart. Enrico Fermi's question, "Where's everybody?" has been rephrased and reformulated in many ways in the 75 years since it was first asked. In the context of the megastructure search, it can be stated with specific precision. If intelligent civilizations tend to grow in their energy consumption, and if the logical endpoint of that growth is the construction of stellar-scale energy-harvesting infrastructure, and if even a small number of civilizations in the Milky Way have begun this process millions of years before us, then the galaxy should contain objects we can see, in a wavelength range we now know how to look in. We should have found something by now. We have not. The temptation, when confronting this fact, is to interpret it as a statement about the universe, as evidence that intelligent life is rare, as confirmation of one or another of the proposed resolutions to the Fermi Paradox, the Great Filter, the Dark Forest, the Zoo Hypothesis, the proposition that technological civilizations reliably destroy themselves before reaching the stellar scale. Each of these ideas has a legitimate place in the discussion. Each represents a genuine possibility that cannot be ruled out by the current state of the evidence. But none of them can be confirmed by the absence of detections from a search that has covered a tiny fraction of the galaxy over a few decades of active investigation. The inference from we have not found one within 1,000 light years to they do not exist is a very large logical step that the data does not support. What the data does support is a much more careful statement. We have not yet found evidence of a Dyson Sphere. The universe, within the limits of our search, has not revealed this particular class of object, whether that is because such objects are absent, because they are rare enough that our local sample has not captured one, because our instruments lack the resolution to confirm them, or because they look different from what we have been looking for. These possibilities cannot currently be distinguished from one another. This is not a failure of the search. It is the expected result at this stage of investigation. The history of astronomy is full of classes of objects that were theoretically anticipated but not observed until the right instruments became available. Black holes, neutron stars, gravitational waves, exoplanets themselves. All of them were theoretically possible for decades before being detected. None of their delays in detection were taken as evidence of their non-existence. They were eventually found because the instruments improved, the methods became more sensitive, and the searches became more systematic. The Dyson Sphere search is at an earlier stage of that arc than any of those examples. The first genuinely systematic, large-scale survey was published in 2024. Its main result, that 7 anomalous M dwarfs were found and subsequently found to be more likely explained by background galaxies, is, from this perspective, a methodological success as much as a null result. It identified the problem. It characterized the contamination. It built the pipeline. It set the upper limits. There is a philosophical dimension to the silence that goes beyond the technical. The Fermi Paradox, in its deepest form, is not just a question about alien civilizations. It is a question about the relationship between intelligence, time, and scale. It asks whether the kind of intelligence that arises on a planet solves its local problems and begins to reach outward, whether that kind of intelligence is common or rare, durable or fragile, expansive or self-limiting. We have exactly one data point. Ourselves. We are a civilization that has been capable of radio astronomy for roughly a century. We are a civilization that is currently consuming about 18 terawatts of power, roughly 1/200,000 of the amount that a Type 2 civilization, by Kardashev's definition, would require. We have not yet begun to harness our star in any meaningful sense. We are, in the language of the Kardashev scale, a Type 0.7 civilization, a young species, still on the surface of a single world, whose cosmic footprint is, from a distance, essentially invisible. If there are civilizations in the galaxy that are millions of years older than us, we should not expect them to think or behave as we do. We cannot confidently project our own assumptions about energy use, expansion, communication, or survival onto entities whose history dwarfs ours by orders of magnitude. The silence might mean there are no such civilizations. Or it might mean that they exist and are simply not engaged in the kind of large-scale visible engineering that our search strategy is designed to detect. Both interpretations remain open. What we can say with confidence is this: the search has not failed. It has begun. The methods exist. The data is accumulating. And the community of researchers who work on these questions is small but rigorous and growing. Upper limits have been set. Contamination sources have been identified. The next generation of instruments will look deeper, with finer resolution, across a wider portion of the sky. And there is something worth acknowledging, in closing, about the position humanity occupies in this story. We are a species that, In the span of a single century, moved from the first radio transmissions to building space telescopes capable of measuring the brightness of stars at 1,000 light years. We are a civilization that has, within living memory, identified thousands of planets around other stars, measured the distance to 1 billion stars with sufficient precision to search for megastructures, and developed the data pipelines to systematically examine 5 million stars at once. We are also a civilization standing at the beginning of a long expansion in energy use, if we survive it and if we choose it. The same questions we are now asking about distant civilizations will eventually be asked about us. Whether future astronomers, ours or others, will someday examine the infrared signature of our sun and find something anomalous, there's a question about decisions we have not yet made. The silence in this light is not only a scientific problem, it is also a mirror. It reflects the question back toward us and asks what kind of civilization we intend to become. The universe is approximately 13.8 billion years old. It contains between 1 and 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. We have searched a small sphere of space around one of them for a few decades with instruments that have now been retired. We have not found the Dyson Sphere. We have not finished looking.